Okay, hello, welcome to this session on reciprocal trig functions and their graphs. So we'll just have a quick look at the basic graphs. Here we are. Here's y equals sec x. That's 1 over cos. And hopefully you can envisage why that's 1 over your cos. I'll just make out the cos graph there. Here's y equals cosec x. That's what it looks like. And that's 1 over sine. 1 over tan is cot. And there you go. Well, we're going to look at these graphs in a little bit more detail now individually. Okay, let's have a look at cos and sec. Well, we know cos. There we go. There's the cos graph. So we're looking at that between around negative 10 and positive 10 radians. So we can see here, there's cos going down. There we are, there's pi. There's 2 pi, so it makes more sense. Negative pi, negative 2 pi. And if we take 1 over that, so you imagine what happens when you divide everything by 1. So here it's actually on 1, so 1 divided by 1 is 1. And there we go. So we can see here 1, and as cos gets smaller, this increases. When cos goes through 0, we have no value. Really, we could have an asymptote there. We could have asymptotes there as well. Everywhere where cos is 0, sec has no value. So sec is 1 over cos. And we need to know and understand and be able to recall these graphs. Okay, let's look at sine and cosec. There's sine, you recognise the shape. It starts at 0, 0. And you think about the principal period between 0 and 2 pi, which you can see. But 1 over that gives me cosec. And that again, hopefully you think about the values that sine give. You do 1 divided by that and you get the pattern you would expect. When sine x equals 0, so at 0, pi, 2 pi, cosec has no value. Again, you need to know this graph. Okay, let's look at tan and cot. Cot is 1 over tan. Let's just remember that tan is sine over x, so cot is cos over sine. There's tan. Recognise the shape. It's rising. But then every pi rads, you get an asymptote. So the first one is at pi over 2, pi over 2, 90 degrees, so at pi over 2 you get an asymptote. That's when sine over cos has no value. Let's have a look at cot though. Cot is 1 over that, and that is your shape. Hopefully this makes sense, and that's another one you have to learn. Okay, well, using a sketch of the graphs y equals cosec x and y equals x, deduce a number of solutions to the equation cos x minus x equals 0 between, well, in the interval negative pi and pi. Well, I've provided a little graph. Thanks again to Desmos. This is really useful. I hope you are using it yourselves. So I've just put in x equals negative pi and x equals pi, so you can see the interval very clearly. There is cosec. We know it starts at 1. The minimum value of this bit's 1 and it's just going to get bigger. The maximum value here is negative and it's just going to get smaller. This is y equals x. Now, we can see here these graphs meet at 4 places. Well, why is that relevant? Well, they're relevant because I can rearrange the equation to cosec x equals x. Solutions can be shown by when the graphs intersect. There's 4 intersections, and therefore there are 4 solutions between negative pi and pi. So you will see questions like this, and this is what it's looking for you to do. If you understand the cosec graph and you can draw y equals x, you can deduce the number of solutions. You don't need to know them, you just need to deduce how many there are. Okay, so you're asked to draw some graphs, and we're going to use our transformations of graphs. Firstly, let's have a look at what cosec looks like, because we need y equals cosec 2x. You need to be able to sketch this. I'm cheating a little bit by using Desmos, but for this demonstration it makes it look nice and clear and it's better than my sketching. So that's what cosec looks like. So I'm changing the input. So this is like going from f of x to f of 2x. Well, what happens? Let's compare them on the same screen. Look at the blue graph. The blue graph is squashed in the x direction. Well, we describe that as a stretch of scale factor of half in the x direction. So everything is half the distance away from the x-axis that it once was. So, rather than having this, your cosec, everything stretches in. So in 360 degrees, you would get the pattern that you would have had in 720 degrees. You get 2 periods instead of 1 in the interval 0 to 360. So it's a stretch scale factor of half from the original cosec. So think about drawing cosec first, and then on your next sketch, you can just do a stretch of scale factor of half. Okay, next problem. Y equals sec x is there. What about y equals negative sec x? Well, negative of the whole function, negative fx, is a reflection in the x-axis. There you go. So if we get rid of the red one, we're just left with y equals negative sec x. So if you can draw sec x between 0 and 360, you can just then draw a reflection of that in the x-axis. Now we're going to look at one that takes quite a few steps. Y equals 1 minus 2 cosec x. Well, I'd prefer to think about this as y equals negative 2 cosec of x plus 1. That's exactly the same thing, but I've written it differently. Well, what do we do? Let's think about the steps. Let's think very carefully about the steps. First of all, there's cosec. You can see that clearly between 0 and 300. If I do 2 lots of cosec, it stretches. It's 2 lots of fx, it's a stretch, scale factor 2, parallel to the y-axis. So that there you've got your blue graph. When you've multiplied the whole function by 2, you've stretched its scale factor 2. Now, let's take the next step. I take a negative of the whole function. That's a reflection in the x-axis. So we've reflected that in the x-axis. And the final thing I'm doing is adding 1. Well, if I add 1, it translates 0, 1 as a vector, and that's your final graph. Let's look again. Cosec, 2 cosec, stretch scale factor 2, parallel to y. Negative of that, reflection in the x-axis. And then we translate 1 unit upwards, parallel to the y. And that's your graph. So if you understand the steps of the transformation, these aren't too bad at all. Okay, let's look at the last one. We've got cot of 2x plus 30. See what's happening there inside the bracket. There's my cot, working between 0 and 360. If I go to 2x, it's a stretch. Scale factor a half, parallel to the x-axis. We remember our rules of transformations of graphs. Now look inside the bracket. I'm taking cot of 2x plus 30 now instead of 2x. So we know we're thinking translation, 30 degrees, but to the left. So the whole graph should move 30 degrees to the left, and there it is. So let's just recap that. Start with cot, stretch scale factor a half, parallel to the x-axis, and then let's move it 30 degrees to the left, and there you go. If you're struggling with sketching graphs, get yourself on Desmos. It's really, really good. It's free. Fantastic piece of software. Thank you.